In this lesson, we're going to focus on the equations of motion for one-dimensional kinematics. And I'm also going to show you what each term within the equation means and how to derive them. In the next lesson, we're going to use these equations to answer questions. I met a friend the other day who has done a maths degree, and he showed me how to derive these equations using calculus. And he started off with this expression here. And this means the second derivative of the position with respect to time equals the acceleration. And the acceleration does not change throughout time. And from this starting point, he was able to derive all these equations here. Now, in this lesson, I'm going to take a more basic approach to deriving these equations. And we're going to do so by looking at the position, velocity and acceleration time graphs to get our final result here. So let me first explain what all these terms mean. So imagine we've got a drag race where our track is about 400 meters long, and we've got a car at the start of the race at 0 meters at rest. Something like that. Now our race cars here can only move in one dimension. They're just going down a straight track. And we'll call this direction the X direction. Now initially, our race car is at position XI, which means the initial position. The car's final position will be at XF at the end of the race. Its initial velocity will be represented by VXI here, VXI, which would be 0 meters per second because it's not moving, it's at rest. Its final velocity would have some quantity that's above 0 meters per second in this case. So in this situation, we don't know what the final velocity is. And in this model, we're going to assume that the acceleration along the x-axis does not change over time. And let's call this acceleration 8 meters per second squared. Now you could have a situation where you're measuring a deceleration. So say if this drag car is moving at 50 meters per second and it's slowing down at a constant rate of minus 8 meters per second squared. The initial velocity would be 50 meters per second, 50, and we'll keep the initial position at 0 meters. Its final velocity, when it finally comes to rest, would be 0 meters per second, but we would not know the final position. We would not know how far the race car is going to travel to stop from 50 meters per second at a deceleration of minus 8 meters per second, so we don't know that answer there. But we can use all these equations above, or a combination of these equations, to find this answer. Now these equations of motion will only work in situations where the acceleration does not change over time. So when we have an acceleration time graph with a constant acceleration like this. So imagine you're an astronaut and you're in a rocket travelling up to orbit. You may be accelerating at a constant rate of around 30 meters per second squared during some part of the rocket burn. And this is equivalent to around 3 Gs. So in other words, you would experience a force on your body that's 3 times greater than the gravitational pull on you on the surface of the Earth. So you would feel 3 times heavier. So you might find that the initial acceleration from the launch pad would quickly increase up to about 3g, and then it will be constant for a certain amount of time. These equations of motion above will only work during this constant acceleration, during this time here. But it won't work at the start when the acceleration is changing, and it won't work if, for example, something goes wrong with the rocket and the top capsule is ejected suddenly away from the rocket. If the top capsule is ejected, if something goes wrong with the rocket here, then you would experience a sudden acceleration in a very short amount of time, like this. And then that acceleration may plateau, like that. But in this time period, when the acceleration is suddenly increasing over time, these equations won't be relevant. You can't use them there. But when the acceleration is constant, you can apply these equations. But these equations are actually quite useful because in a lot of situations, the acceleration is roughly constant over time. Now, in a previous lesson, we learnt that the average acceleration is equal to the change in velocity over the change in time. But we also discovered that the instantaneous acceleration is equal to the derivative of the velocity with respect to time, as the difference in time approaches 0, so as delta t approaches 0. But since our acceleration is constant here and doesn't change over time, our velocity time graph changes linearly over time. So the average velocity here is equivalent to the instantaneous velocity. Because if we were to measure the gradient of the velocity time graph using this expression here, where we have the final velocity up here, minus the initial velocity, change in velocity along the x-axis, divided by the change in time, we would get the gradient of the velocity time curve. But if we took the derivative of this equation of the velocity time here, we would get the same value as the average velocity. So what we can do here is substitute the instantaneous velocity into this equation because they result in the same value when velocity is linear over time. We can set the initial time to be 0. And with this equation here, we can transpose it to make the final velocity the subject of the equation. So if we do that now, if we multiply both sides by the final time, we get AXTF is equal to the final velocity minus the initial velocity. If we add both sides by the initial velocity, we get Vxi plus AXTF is equal to the final velocity. This is the first equation in our list up here. So we've got the final velocity of a particle moving at constant acceleration, doesn't change over time, is equal to the initial velocity, whatever that may be. It could be 0. So we could be starting off at rest, or we could be measuring a particle when it's in motion. And we do this over a specified time period. So in other words, if we look at the graph here, what we're doing is we're saying, okay, what's this value up here, given this time here, knowing that the acceleration, in other words, the gradient here, is a constant value with an initial velocity of 0. And this equation here generates this straight line because it's in the form of y equals mx plus c. Now there's another thing worth mentioning about the velocity time graph here that's really quite important. The average velocity of a particle along the x-axis can be represented by the initial velocity plus the final velocity divided by 2. So for example, if you're in a car on the highway and you're initially travelling at 10 meters per second, if you increase your speed to 20 meters per second, your average velocity over those two speeds would equal 15 meters per second. In other words, if this was 10 meters per second at some time, and this was 20 meters per second at a final time interval, your average speed would equal 15 here, which is halfway between the two. And this only works when you have a velocity that changes linearly with time. It doesn't curve up or curve down. But we also noticed in a previous lesson that the average velocity can also be represented by the final position of the particle minus its initial position divided by the time it takes to move between those two positions. In other words, the change in position over the change in time. So we can use these two equations here to derive another equation of motion up here. So from these two equations, we know that they equal one another. So we can say, from the top equation here, the initial velocity plus the final velocity divided by 2 is equal to this equation down here, which is the final position minus the initial position divided by the time. Now we need to transpose this expression here to make one of these terms the subject of the formula. We're going to choose the final position to be the subject of this formula here. So I'm going to multiply both sides of the equation by t, and then I'm going to add both sides of the equation by the initial position. So I've rearranged some of the terms here so that it looks very similar to the equation above, which is this equation here. So that's our second equation. To derive the next equation, we can substitute equation 1 into equation 2. So we can add the left-hand side of equation 1 into this term here, because we've got the final velocity up here. So we get the initial position plus half of the initial velocity plus this term up here, which is equal to the initial velocity again plus the acceleration along the x-axis over a specified time. And just a note here, this final time assumes that the initial time was 0. So in effect, this is saying over over a change in time multiplied by t is equal to the final position of that particle. So all we need to do now is just expand out these brackets here, and we get half of the initial velocity multiplied by time, because we've got time outside the bracket here, plus half of the initial velocity multiplied by time again, plus half of the acceleration multiplied by the time squared. And that is equal to the final position. So half of this component here plus half of the same component equals one of that component. So we get initial position plus the velocity, initial velocity multiplied by time, plus half axt squared, which is equal to the final position, which is the same as this equation up here. For the last equation, we're going to rearrange equation 1 to make t the subject and then insert it into equation 2 here. So subtract both sides by the initial velocity and divide both sides by the constant acceleration. If we substitute this term here into equation 2 here, we bring the final position and put it over here, which is equal to the initial position plus half the initial velocity plus the final velocity multiplied by this term here. Final velocity minus initial velocity divided by the acceleration. Now we can simplify these brackets here by multiplying out. We get the final velocity squared, Vxi multiplied by Vxf minus Vxi multiplied by Vxf minus Vxi squared. These terms cancel. Resulting in the final position, which is equal to the initial position, plus the final velocity squared minus the initial velocity squared over 2 times the acceleration. And we can rearrange to make the final velocity the subject multiplied by 2ax and that's the final equation. Now, in a later video, I'll show you how to use these equations and solve example problems with these equations. Depending on the course you're doing, you might not necessarily need to derive these equations from scratch like this, but you will definitely need to memorize these equations to answer questions in kinematics.